Welcome to our video presentation. This is Team 8's design concept for Design Project 2. This has been completed over the last 12 weeks and aims to demonstrate a potential manufacturing facility which processes a Jenga block.
This video demonstrates all the elements of the design. The process begins with the insertion of the Jenga block into the main hopper. The block slides through the hopper onto the first step of the horizontal walking beam. It then transfers along the beam until the end point where it transfers to the processing area. The Jenga block then moves to the processing area, transferring onto a disc for insertion. The disc rotates the block into an enclosed chamber where the processing will take place. After this process is completed, the piece is rotated back out. The block is then transferred by hand to the stair hopper. The block then slides onto the first step of the stair beam, which transfers the block to the endpoint for collection. The block onto their respective walking beams. The hoppers were implemented to avoid injury when using the device, preventing direct contact with the moving components. The Jenga block enters the hopper with the length of the block aligning with the intake width. The other dimensions will correct themselves easily. The blocks are delivered onto the first step of each respective beam in line with their own tolerances. All pieces of the hopper consist of 3mm aluminium machined using a CNC lathe. This ensures a high degree of accuracy in the machining process as well as a robust intake, as errors in the intake segment are liable to cause complete jamming of the
beam. The walking beam is powered by a singular rotary motor. The motor powers two small plastic meshed gears, powering the pulley's axle. The pulley system rotates, powering the cam discs. These discs have an axle offset from the center of rotation by 25mm, connecting to the walking beam's external walls. As the whole system moves, the outer walls lift up 25mm and forwards 50mm all the way around. While the interior walls remain fixed, the Jenga block is lifted by the exterior walls and placed into each step of the interior walls, one step at a time. Reduced friction acting on the axles and brackets and allow a free transfer of motion between the pulley systems and the cam discs. A ball bearing was implemented into the pulley's bracket, aiming to reduce the resistance and reduce the required torque output from the motor.
We're talking about the stands and fixtures of the walking beam. The walking beam rests on 4 stands, 2 of which are connected to the pulley system, shown on the left hand side, and the other 2 which are connected to the inner stationary wall through M3 bolts. The inner walls are also connected through 10mm aluminium cylinder, which also connects to the frontal stand. The outer walls are connected with aluminium brackets through M3 bolts. The back stand is connected without any fixtures and is instead connected through slots. The beam also features a ramp at the end of the inner walls. This allows the Jenga block to seamlessly come off the assembly line and go into the next section. At the bottom of the walking beam is 9 rubber feet. These would be externally bought in and can be glued into 3mm holes at the bottom of each stand. These feet allow the walking beam to dampen vibrations and to prevent sliding on the surface area.
The rotating disc is comprised of 4 parts. The first part is the base, which is 3D printed from PLA. It's designed to hold the motor with a half millimeter tolerance either side of the motor, so it fits in nicely. And there's also a slot for the motor's wires, so you can access the motor. The clear discs you see are made from laser cut acrylic, and they're the rotating discs that will be moved by the motor in the center. And they'll be stuck together with super glue, creating an indent for the Jenga block that has a half millimeter tolerance either side of the Jenga block, so it fits in smoothly. The bearing in the middle is a bearing you'd find in a Lazy Susan on a table. it has a hole in the middle to allow the motor to turn the rotating discs, and it is load bearing so that the motor doesn't have to be too high torque to move the.
The Jenga block is first placed in the disc. The door then opens, allowing for the Jenga block to be rotated inside the enclosure. The door then closes. Once the door is closed, the process inside can occur. As this is happening, the block on the outside can be replaced with a new one. The door opens, the disc rotates out, the door closes again, and the block can be replaced. This allows for continuous processing and continuous production. Most of the components here are laser cut acrylic or milled aluminium. The door ensures operator safety, and the vent aids to remove light dust and gases. There is an allowable tolerance of 1 mm for all parts.
The basic principle of the walking stairs is to move a Jenga block from point A at the bottom of the stairs to point B at the top. This is to show how a part being processed in a factory would travel along a diagonal walking beam that would displace it upwards and move it onto a separate area of the factory. Some of the key tolerances taken into account for the design is the angle design for the Jenga block to sit in and prevent it from falling out. The design of the stairs is made so the Jenga block has a high tolerance off each side so that the edge can be picked up by the rotating stairs on each side with minimum error, and the rotating part has the corners cut off it to allow for no accidental contact during the rotation. The Jenga block is placed on the first step of the walking stairs where it will begin its ascent. The motor is switched on and the side panels rotate towards the top, picking up the Jenga block on the second stair of the rotating panels and moving it up to the second stair of the stationary in the center, repeating this until the Jenga block reaches the top.
An axle located at the top of the diagonal walking beam is driven by a motor, which powers an initial pulley of the same diameter through a belt. This top pulley connects to another system via additional belts, linking it to a bottom pulley, which also shares the same diameter. This configuration ensures that the axle and both pulleys rotate at the same speed. The setup is designed to efficiently transfer torque and maintain consistent speed control for the side panel, enabling precise operation in line with the Arduino code. The walking beam is made with various components crafted from different materials. For in-house manufacturing, we'll use aluminium and 3mm acrylic. All acrylic parts will be precisely cut using a laser cutter, while aluminium components will be machined using a CNC lathe. This approach ensures high quality production and consistency for each component of the walking beam.
This design was created during our first semester of our Design 2 module, MEC 3020. In Semester 2, we plan on putting these concepts into action, ordering our parts, building prototypes, and implementing Arduino electronics to make this final model of our Jenga block manufacturing process. Thank you for listening to our design concept for our Jenga manufacturing process.